Okay, so now I'll record this for those that aren't here today so they won't miss anything. So we looked at finding antiderivatives, and but at this point we really don't know. We saw those little integrals, and we don't really know what's going on or what those do actually. Well, today we're going to kind of get an idea about what an integral does. When we integrate something, what's going on with it. But before we do that, we have to, I want to look at something called summation notation, which you've all seen before. But an integral is a sum. What you're doing with an integral is you're summing up an infinite number of very small things. Infinitesimally little small, tiny, tiny things. So that's what we're doing with integrals. So involved in defining what an integral is, we need to talk about summation notation. Now, so here is, let's just look at this. Let's suppose that we have 1 plus 2 plus 3 plus 4, like that. And I don't want to write it out that way, let's say. I want to represent that another way. So what I could do is I could use this Greek letter, sigma, and I could represent these numbers with some kind of generic variable, let's say. So maybe k. And I could say, okay, well, it looks like k starts at 1 and goes to 4. And this is how we could represent this with summation notation. Now, what this means, if you look at something like this, here's what it means. Now, I'll do something different here. I'll say, well, let's say k, let's look at one where k goes from 2 to 5. And let's suppose that k, I've got k squared, something like that. So we'll just look at a formula like this. Now, here's what this means. You start at this bottom, this index here, and you put in the 2. Okay, so this is 2 squared. And then immediately you put a plus. You always put a plus. Then you increment it to the next integer, okay, which is 3. So this would be 3 squared. And a plus. And then the next integer, 4 squared. And then finally you go until the 5 squared. And that right there, these two things say the same thing. 2 squared plus 3 squared plus 4 squared plus 5 squared. Okay? So this is how we can, this is just another notation that we can use. Okay? But it's just a way we can sum things. Any questions about that? Now, let's just look at a couple of things here. Let's suppose that we've got something like this. And I'll change my notation to I, let's say. And I want to start I at 1 and maybe go up to 4. And I'll do this. I'll say I squared plus I cubed. And I'll just put that all in parentheses. Now, just doing like what we did up here, we're going to start off with 1, and we take 1 squared plus 1 cubed. Okay, there's the first thing. Then we increment it. 2 squared plus 2 cubed. Okay, we're going to increment that. 3 squared plus 3 cubed. And then one more, we're almost there. 4 squared plus 4 cubed. Okay, so now obviously, I mean, that's just using what I told you about summation notation. That's how we do that. What we're going to look at here is a property of summation notation. And the property is this, that it doesn't, we don't have to, we can give each one of these its own sum. In other words, I could have summed I squared and then added that to the sum of I cubed. In other words, look at this. Let me just group all the I squareds together, or the squareds together. I've got 1 squared plus 2 squared plus 3 squared plus 4 squared. You know, we're just adding these up, so it really doesn't matter how I order them. And then I'm going to put the cubes, right? So I've got 1 cubed plus 2 cubed plus 3 cubed and 4 cubed. Now, look at this. This right here is just You know, we're just saying I goes from 1 to 4 of I squared. That's what that is. And this over here is just I goes from 1 to 4 of I cubed. So the idea is that, or the point I'm trying to make here is when we're talking about summation notation, we can do this. We can say if I've got something I'm summing up here, let me just call it A sub n plus or minus B sub n. And I have n goes from, I don't know, I'll just start at A to B. I mean, not A to B, that wouldn't be a wise choice. Let me just say 1 to 4. It's not as general, but it's, you know. So what we could do is we could say, well, I can split that up. And the n from 1 to 4 doesn't matter. It's just whatever it is, whatever n is. And plus or minus. Okay, does everybody see that? Now we could be a little more general with it. We could say, okay, we could say summing over n, whatever n may be. You know, A sub n plus or minus B sub n. This is the way we could be a little more general. It's the sum over n of A sub n plus or minus the sum over n B sub n. There's the way we could be a little bit more general. Okay? Any questions about that? Okay, so that's one of the properties of summation that we want to look at. And then let's look at another one here. Let's suppose that I'm going to sum, and I'll use j this time. Usually when we're talking about these sums, we'll use as the variable that we increment, I, j, k, or n, usually, lowercase. So let's suppose I want I equals 1 to 3, and I have 4 j squared, something like that. Well, notice if I keep that 4, I've got 4 times 1 squared plus 4 times 2 squared plus 4 times 3 squared. See, that 4 really didn't do anything. It's just kind of tagging along for the ride. And you know that I could factor that 4 out. I could factor the 4 out and get 1 squared plus 2 squared plus 3 squared. There's no problem in doing that. Well, look at this. This part right here is exactly the sum. The sum, whoops, let me give myself some room here. The sum, as j goes from 1 to 3 of j squared, and I could just put the 4 on the outside. In other words, the idea is that you can factor out a constant. Okay? So if you've got a summation, and you're summing over some j, and you have a constant times, well, let me put a j there. And you've got a j here. I can factor out that c. Okay, like that. You'll see that? Okay. Any questions about that? So this is old, right? You've seen this before. And this is just me refreshing your memory. Now I want to show you something that might be a little new to you. And we're not going to use this, but I just want to show you so you'll say, oh, okay, I see something new I didn't know before. You can have double sums. Okay? And maybe let's just look at how this would work. Let's suppose that this is j goes from 1 to 3, and this is k goes from 1 to 2. Okay. And maybe I'll have something in here like this. I'll have a sub j and b sub k. I want to show you how something like this. Now this is something we're not going to work on a lot. I'll just show you how it works. What you do is you take the sum that's on your far left, and you increment that. And then you sum through the k's. So dig this. Here's what's going to happen. I'm going to let j be 1. So a1, b1, right? And then plus, I'm keeping j at 1, and now I'm going to the next k. There, look at that. So I incremented j, and I went through the k's. Now I'm going to increment, well, I kept j constant. I've kept it fixed. Now I'm going to increment j to be 2. So now look what's going to happen. A2, B1. A2, B2. Okay? You'll see that? Now I increment j again, and I get A3, B1 plus A3, B2. Okay? So you can have double sums. You probably won't see that for a long time. If you take Calculus 3, a lot of times you'll see a double sum thrown in there. Okay? Any questions? Okay, so there is just a review about summation notation. Now, sometimes you'll see something, sometimes we're interested in being able to calculate the total, the sum, without having to actually add up everything. For example, a famous example is, what about if you want to figure out what this is? And you add up all the way to 100. And you want to say, okay, well, what is that sum? Well, that's time consuming if you try to do it without being clever. If you just say, okay, 1 plus 2 plus 3, and you add up all that, that's cumbersome. Now, one of the things you could do, and like I say, this is kind of a popular example, you could say, well, what about this? This is the same thing, isn't it? Whoops, plus 1. That's the same sum, isn't it? I'm just listing it backwards. So I've got the sum, here's the sum, and here's the sum. These are both the same, right? You might say, why would you do such a thing? Well, because I could add these, right? I could say, well, I could double the sum. In other words, add these two, right? 100 plus 1 is 101. Okay? So I'm just adding these, and what I get is twice the sum by adding the pairs of numbers. 99 and 2 is 101. 98 and 3 is 101. My goodness, they're all 101s. All the way down here, look at that. I have all those 101s. Now, that's twice the sum. How many of those 101s are there? Huh? Dalmatians? 101 Dalmatians. Now, how many are there? There's 100. Yeah, there's 100. So 2s equals 100 of these bad boys. Now I divide by 2 because I don't want double the sum. I want 1 times the sum. And what I get is I get the sum is equal to 100 times 101 over 2, right? So that's the sum, right? It's 50 times 101. So that, notice we didn't have to add up everything. We were just clever. Now, there was nothing special about 100, adding 1 to 100. I could just do this. I could say, well, I'm going to do 1 plus 2 plus 3 plus 4 all the way out to n. I'm going to add up n of these. And then I could go back and I could do the same process. Let's see here. How would I do that? This would be n, okay? This right here would be n minus 1, wouldn't it? Right? It was 100 and then 99. Well, now I have n plus 1. And this one right here would be n minus 2, n minus 3. What would this be at the very end? Huh? What would it be at the end? Would it be 1? I think it would be 1, wouldn't it? See, it's going to be, I think it would be that, wouldn't it? Now, okay, let's add these up like we did before and see if we can get up with 2 times the sum. Okay, n plus 1 plus, this is n plus 1 as well. Look at that, n plus 1. Oh my goodness, all of these are adding up to n plus 1. Look at all those n plus 1s. Yeah. Now, how many of those are there? There's n of them, right? Yeah, there's n. Now, if I, so look what I got. I got 2s equals n of these n plus 1s divided by 2. And look what you get. You get a nice sum here. Look at that. So if you tell me how far you're adding or how far to go, I can tell you what the sum is. So that's cool because I could do this. I could say, okay, let's see about this. Let's suppose I've got the sum, and I'll use k this time, from 1 to 50. And I've just got k in there. Well, what this is telling me is I'm going to put 50 times 50 plus 1 over 2. See? Because I'm starting here at 1 and going to 50. So that's the sum, you know. And you could work it out, but this is 51. Now, we're not going to actually be, and of course that would be 25 times 51. We're not going to be doing a lot of this computation. We're doing this because what I'm trying to do is get you ready where I can define the definite integral for you. And it's going to require these sums. Okay, any questions about that? Now, here's what we know. We know that if you take k goes from 1 to n of k, we know that's n times n plus 1 over 2. We know that. Now, there's some others that I'm just going to give you. We also have other formulas. We've got k goes from 1 to n, where this is k squared. This is going to be n plus 1, 2n plus 1 over 6. Okay, now let's look at one more. Okay, let's suppose that we've got a cube, n, and this is k cubed. Well, that one is going to be, oops. I believe it's this. Let me see. I believe it's n squared times n plus 1 squared over 4. I believe that's it. Okay. So these are the ones that we want to memorize those because we're going to be working with those. Okay, any questions about those? Okay, now let me put, yeah. Okay, so this is what we want to remember, these sums. Okay, so now here's what we want to do with this. What we want to do is we want to kind of change gears and talk about finding areas under curves. Okay, so that's kind of what we're going to use for these sums. Let me show you how we'll look at it. Okay, so here is area, and let's suppose that we've got a function here. Let's suppose we've got this function f of x equals x squared plus 1. Or I tell you what, let's do this. Let me just do x squared. And what I want to do is I want to go from, on this interval, I want to go from 0 to 6, and I'm going to break up this curve, the x's underneath that curve from 0 to 6 into, let's say, 3 equal parts. The 3 equal parts. Okay, now, if I do that, here's what's going to happen. If I want to break up that interval from 0 to 6 into 3 equal parts, I want to know, well, what is the width of each one of those parts? Well, I'll call that delta x. And that's going to be 6 minus 0 over 3, right? I take the width and divide it by how many equal parts, and I get a 2. Okay? Now, I'll say that's my delta x. Now, let's look at this. Now don't pay any attention to the grid here, because in fact I think I'll get rid of this grid. Let me just go to view and just do lines, because I'm not going to be accurate here. So we'll start off with 0, and I would go up 2. So here's 2. I go 2 more. There's 4, and then up here is 6. Okay? And of course, our graph, it just looks like this. Now here's what I can do. I'm going to come up here at the 2 until I hit the graph and then go over like this. Okay? And then I come up here and go over. So what I'm doing is I'm making little rectangles. Okay? So I come up here and go over. And I've got 3 rectangles. You might be wondering, why are you doing this? Well, now I'm going to explain. Let's suppose that I'm interested in what is the area under this curve from 0 to 6. I'm interested in that. Well, I don't know how to calculate that. I mean, it's a curve. I don't know how to get the area under that curve. I can deal with circles and some curves, but not this one. But I do know how to get the area of rectangles. So I'm going to calculate the area of these rectangles, and then I'm going to say, okay, that's an approximation for the area under that curve. That's what I'll say. Okay? So let's see what I can do. Okay, now I'm going to calculate the area of this first rectangle. Now this first rectangle is 2 times f of 2, right? So we've got the width and we've got the height. F of 2 is the height. Okay, does everybody see that? Now, f of 2 is 4, but let me just leave it like that for now. Now, let's go to the next one. The width here is 2, and now I have f of 4, right? F of 4. And then the next one, the width is 2, and I have f of 6. So I've got all of these rectangles here. Now, that's going to be more area than I need, because the area under that curve is obviously not the same as that. That's too much. But I want to point out something here before I actually calculate this. What if you look at this first one, you've got this 2. This is my delta x. So I'm just trying to generalize. And look what I've got here. I've got f of 2. Now, let me do this. This is 1 delta x, right? Okay. So just bear with me here. This is 1 times delta x. Now this next one, I've got delta x, and that's 2 times the delta x, right? Because we just started at 0. And the next one is 3 times delta x. Right? That's a way I could kind of generalize what I wrote there. Okay? Now, I just wanted to point that out to you. Just point it out to you. And notice what delta x is. Delta x, let's go back and reflect a minute. Delta x is really the width of the interval over n, right? In this case, I did 3 divisions, so there you have it. Do y'all see that? Okay, now let's go back down here and actually calculate what this is. This is going to be, let me factor out a 2. So I've got f of 2 plus f of 4 plus f of 6. Okay. Now f of 2, so I've got 2, f of 2 is 4. This is 16, and this is 36. Okay. So what is that going to be? 2 times, let's see here, is that 56? Is that whole thing 56? Because I've got 36 and 4, that's 40. Yeah, I think that's 56. So that's going to be 112, right? Now, 112 square units, that's more area than is what is under that curve, right? That's too much. I wonder if we could get a better estimate if we did this. What about if n is equal to 6? If n is equal to 6, we might get a better estimate, because let's just see how that would look. We've got 1, 2, 3, 4, 5, 6. And now, so I've divided this thing up. Now, look. Does it look like we're going to have less error? Now, just use your imagination. If we use more and more of these divisions, this part up here is going to get smaller and smaller and smaller. In other words, the amount of area that's more than we need is going to get more and more tiny, right? Tinier, okay? That's what's going to happen. We can see that coming. Now, if I were going to calculate this, let's think about what would happen here. This first one is going to be 1 times f of 1 plus 1 times, because that's delta x now, right? This is f of 2 plus 1, f of 3 plus 1, f of 4 plus 1, f of 5 plus 1, f of 6. Is that right? 1, 2, 3, 4. Yeah, there's 6 rectangles. Now, so we could calculate that. I don't want to calculate it right now, but does everybody see that that would give us another approximation? Okay, now, let me see if I can generalize this. So this 1 is my delta x, isn't it? Okay. Now, let me do this. Let me be a little bit fancier. Instead of calling it delta x, let me call it 6 over 6, right? 6 over 6. You might think, that is insane. Why are you doing that? Now, what is this first one? This is 1 times 6 over 6, right? That's what f of 1, okay. Now let's look at this other one. We got 6 over 6, f of, now what is this one going to be? Huh? Is it going to be 2 times 6 over 6? Okay. And this next one is 3. Well, let me be consistent here with what I'm doing here. Because what we're doing, this may seem mindless and just absolutely ridiculous, but this is going to be 3 times 6 over 6 plus 6 over 6, 4 times 6 over 6 plus 6 over 6. Okay, let's keep going here. F of 5 times 6 over 6. And the grand finale is 6 over 6, f of 6 times 6 over 6, which is f of 6, right? Which is, you know, this is this, right? So see, we're just being general now, right? And, okay, so this is very important. As we increase the number of rectangles, the number of divisions, we get a better estimate of the area under that curve, right? That's for sure. Now, let's be general. Let's just say there's n rectangles. Okay? Let's suppose there's n rectangles. Okay? Let's suppose we have that. Well, then delta x, isn't delta x just going to be 6 over n? Do y'all see that? Then let's look at our sum. Our sum is going to look like this. 6 over n times f of 1 times 6 over n, right? Plus 6 over n, 2 times 6 over n, right? All the way, you know, we've got n of these things. So this is going to be 6 over n, f of, well, what's going to be the very last thing that we do? N times 6 over n, right? Which is f of 6. Do y'all see that? Now, what you're about to behold is extremely cool, because this is a general form for that summation, right? For n rectangles. Now, let's write this in summation notation. I'm going to use k, and k is going to go from 1 to n. Is that right? So here's what's going to happen. I've got 6 over n, f of k times 6 over n. Yeah, 6 over n is just a constant. It's not going to change. It doesn't matter. Now look, here's what 6 over n is. 6 over n is delta x. It's delta x. Now, I'm going to rewrite this bad boy right here. And here's what I'm going to do. Since we're dealing with x squared, I've got this. I've got k equals 1 to n. And this is going to be k times 6 over n squared times 6 over n. Does everybody see what I did? Because f of x is x squared, right? So instead of saying f of k 6 over n, I'll just say k 6 over n squared. That's dandy, right? Okay, now let's see what we got now. Now, okay, so watch this now. I'm going to square this, and let's see what we've got. If I, okay, there we go, n. Okay, if I square this, I get k squared times 36 over n squared. Y'all see that? Now, you can see the bottom is n cubed, right? Now, let me just leave it. Let's just leave it right there. This whole thing is not going to change. However, we know how to write the sum of k squared from 1 to n, right? What is it? It goes like this. It goes n times n plus 1 times 2n plus 1 over 6. Does everybody see that? That's our formula, right? Now, I'm not finished because this is 36 over n squared times 6 over n. I don't have the summation anymore. I don't, right? Because I've calculated it. This is it. This is the summation. K squared, as k goes from 1 to n, that is given by this formula. We've established that earlier. Now, let's take a minute and look and see what happens here. Now, notice that these sixes, these sixes here will cancel. That's nice. That's a nice thing. And now, here's what I want to do. I want to multiply out the top. I've got 36 here, but let me multiply out the top. I've got n squared plus n times 2n plus 1 over n cubed. Does everybody see that? Now I'm going to go ahead and multiply that out, although at this point, let me go ahead and multiply it out. So what I'm going to get is I'm going to get 2n cubed plus n squared, okay, plus 2n squared plus n, and all that over n cubed. Y'all see that? See what I did there? That was just algebra. Now remember, this right here is that sum. So if you tell me what n is, I can tell you I can give you an approximation for that area under the curve. Now, 2 times 36, that's about 72, isn't it? Now, I won't write that yet. We know that's 72, right? Now, we said as you let the number of rectangles get more and more, the error is going to decrease, right? Because the error, the error is just that little bit of extra there. Now, let's look at this. Okay, well, what if we do this? What if we let the number of rectangles go to infinity? Let there be infinite number of rectangles. Well, we know how to evaluate that, right? This is a limit to infinity, and remember, I should have combined those. although it doesn't matter. And this is like horizontal asymptote, right? If the degree on the top and the degree on the bottom are the same, then the limit is the ratio of the leading coefficients. Well, look at that. Up top you have 72, and on the bottom you have 1. So this limit is 72. That's what we're saying. That limit is 72. Here's what we're saying. Okay, the error decreases as you get more and more rectangles. I just let the number of rectangles go to infinity, and I added them all up, which is a miracle that I performed in front of you. And I get 72. And apparently I'm claiming that is the area under this curve. Okay? That's what I'm claiming. Now I want to give you a little bit of insight into where we're going with this, because this right here is how we're going to define a definite integral. We're going to define a definite integral in terms of a sum. Now let me show you something amazing here. Let's look at this integral. And I'm going to go from 0 to 6. And I've got x squared dx. The antiderivative of x squared is 1/3 x cubed, right? So watch what I'm going to do. I'm going to do 1/3 x cubed, and I'm going to plug in a 0 and a 6. Now we're going to dwell on this more later. This is just an overview. I'm going to put in a 6. So I've got 1/3 times 6 cubed, and I could say minus 0, right? Now what is 6 cubed? What is that? That's a big number, isn't it? What is it? Well, I don't know. Let's see here. Maybe we can do it this way. Maybe we can say 6 times 6 squared over 3, and that's 2 times 36. 72. Ah, look. Do you see that? This integral right here seems to be acting like an infinite sum, doesn't it? And that's evaluated at from 0 to 6. So look, I put 6 in, and then I could subtract off plugging in a 0. We're going to look at that more later, but what my point is, we did these antiderivatives, and you can see now, I bet there's a relationship between these antiderivatives and infinite sums, because this right here, this is an infinite sum. Now, this is easier to write than this, right? This right here, this is a definite integral. I mean, this is how we define it. We're going to define the integral from 0 to 6, x squared dx, this way. This is, well, with a limit. The limit as n goes to infinity. That's the way we're going to define it. Okay? How does that grab you? That's good, right? Good way to finish the week.